Hello, everyone, and welcome to today's webinar, The Moon and Beyond from a Thermal Perspective. I'm Amanda Hosey, your moderator for this 60-minute program, which focuses on mission-critical thermal management strategies. Our speakers today are Bryan Muzyka and Jimmy Hughes of Advanced Cooling Technologies, or ACT. As the Vice President of Sales and Marketing, Bryan leads the sales and marketing team at ACT and serves as a board member on the Keystone Space Collaborative, a nonprofit organization building the space ecosystem in Pennsylvania, Ohio, and West Virginia. Bryan holds a bachelor's degree in mechanical engineering from Penn State University and an MBA in engineering from Lehigh University. Jimmy is the lead engineer in ACT's Orbital Space Systems product development team. He has played an instrumental role in pioneering technologies for two-phase microclimate cooling systems and successfully developed multiple products from concept to reality. Jimmy holds a bachelor's degree and a master's degree in mechanical engineering from the University of Central Florida. If you have questions for our speakers, please send them to the Ask a Question box and we'll address as many as possible at the end of the program. Also note that a PDF of today's slides may be downloaded under the Event Resources tab on screen. Now, onto the presentation. Welcome, Jimmy and Bryan.
Thank you, Amanda, the SAE media team, and all the audience members. Appreciate you guys joining us today. Today, we have kind of a presentation giving a very quick overview into who ACT is, and then talking more in depth on a couple different case studies in the spacecraft thermal control area. So for those who aren't familiar with Advanced Cooling Technologies, we are a small business of around 250 employees in Pennsylvania. We have two facilities in Lancaster and York, Pennsylvania. We do a fair amount of work in defense, aerospace, and industrial products, so really focusing on anything that has critical thermal management challenges. And over our history, we've won several product innovation awards, as well as customer supplier awards and government awards through NASA, DoD, and DOE organizations. So very proud of the work we do for our customers and for the government. And yeah, hopefully you guys get a good sense of available technologies that we offer. And please feel free as we go to ask any questions. We'll get to a lot today. We hope to give you back some time of your hour and get through everything rather quickly. But please ask as many questions, and if we don't get to them live, we will respond via email and/or set up a time to discuss in more detail. Again, just on company background, we are ISO 9001 and AS 9100 certified. So we have all the quality systems in place to execute programs on the defense, aerospace, and very critical national security programs. So we do almost all custom products, so we have a very robust routine of design through production capabilities. We also want to thank all our partnerships with our customers, and a special thanks to NASA and Space Force, who have funded a lot of the developmental technologies you'll see here today and have helped us in the commercialization of those technologies. So through SBIR and commercialization programs associated with those, we have been able to advance TRL in many of these technologies and ultimately bring them to a broader customer base. So certainly want to thank all our supporters, whether it's direct customers or the government. And from a product portfolio, because we felt this presentation was somewhat focused in a couple key areas that we're receiving a lot of more recent inquiries, we wanted to share kind of the broader sense of our product offering as well. So while we won't go into a lot of the detail here, the focus will be more on spacecraft thermal control, system level thermal control for space. We do want to kind of show our total offering, so if audience members are more intrigued or also do work similar to us in terrestrial programs as well as space, we do have a broad offerings of active and passive cooling options for those type of systems. Also did want to mention a couple different technologies that we won't focus on today, but the space community has been showing a lot of interest in. The first being the top left, high K plates, which is high thermal conductivity plate. Because today's webinar focuses a lot on the system level side, Did want to bring this up. This is used more at the component or board level cooling applications, but getting heat from specific FPGAs or chips out to the rails that can ultimately be heat transferred out to the radiators and dissipated to space. We also have versions with water-based solutions, refrigerant-based solutions, ammonia-based solutions. So a lot of different options there from a fluid perspective in those high thermal conductivity plates. Also have more constant conductance embedded heat pipe solutions as well as pulsating heat pipe designs. The next one I'll touch on is the second one in line there, the phase change material. Again, this is used more at component level, but for thermal storage. So as you go into unique orbital profiles or landing missions, if you need to absorb energy for a short period of time, or if you have duty cycle applications, this is used, is being considered a lot in space applications for its ability to absorb energy and then dissipate it over a longer cycle. So many of the technologies we'll talk about use two-phase heat transfer, liquid to vapor. This uses solid to liquid latent heat of fusion to store energy, but again, used very well in those short duration missions or pulsed applications and can create a much more simplified thermal management system than designing towards those peak powers. So again, just to kind of show the breadth of ACT, because space is very unique, we do almost exclusively custom thermal solutions. So with that, we have a lot of capabilities built around our analytical capabilities, our testing capabilities, prototyping, but we do have the ability to scale those up to production as well. So kind of offer the full gambit, and I would say the big value add, and we'd be happy to talk more on specific applications, but is our ability to shorten the design cycle with our in-house code and two-phase knowledge to really work with the commercial thermal desktop and CFD tools, but be able to short circuit those design cycles with our either background knowledge, IP, or in-house code to complement those softwares. And just another look at kind of the overarching areas of ACT. So we do a fair amount that we'll talk about today in space, particularly here on satellite cooling, but then we have the complete infrastructure for ruggedized and harsh environment cooling on the terrestrial ground-based system side as well. So you can see a lot of different applications there. In one specific example of a large Space Force communication application using phased array radars with satellite communication and ultimately data processing servers nearby as well. And I mentioned this, but we do have a lot of in-house capabilities on spacecraft thermal analysis. So whether it's thermal desktop, which is used frequently in the industry, or commercial CFD tools, we do a lot of verification through analysis, and we have those capabilities to do not only component level cooling, our product integration, but also orbital analyses, landing missions, things of very complex thermal profiles, and able to analyze all the worst cases to make sure ultimately that our products are going to work in space. So today, just looking at a little bit of the agenda, we're going to talk, I'll talk through a little bit on the active system level thermal control, and then Jimmy is going to be providing his expertise on lunar thermal challenges with surviving lunar night specifically, and then we'll talk about a little bit more about our work in supporting future nuclear power generation on in a lunar environment as well. So to kind of start, active thermal control systems, we're going to talk a little bit more about this from a satellite perspective, looking at some of the design considerations associated with implementing an active thermal control system, talking through some of the challenges and regimens associated with pump fluid loops, and then talk through a couple of the key technologies, and especially the technologies that ACT has provided for spaceflight. So the first area we wanted to talk through is when to consider active thermal control systems. So the vast majority of spacecraft being used are leveraging passive thermal management solutions, things like conduction, radiation, heat pipes for heat transfer, and various other passive. Obviously a very strong solution because passive does lend itself to high reliability, no moving parts, no failure mechanisms. So it is an ideal solution, and we certainly want to promote the passive cooling route as much as possible. However, there does become a point, and usually dictated by total power, when it does make sense to consider active pump fluid loops. So again, most cases we're going to try to design using more traditional heat pipe, heat transfer, radiator systems to reject the full heat load. But in certain cases, once you get high enough, the mass trade-off from implementing such robust passive technology solutions would tend to favor a pumped liquid solution for mass saving. And typically, there's a lot of complexities in those analysis and trade-offs, but usually we'll consider active somewhere above 10 kilowatts. So while passive solutions have gone well above that threshold, you really want to start analyzing the geometries, the complexities, the mass trades at around 10 kilowatts and make those trade studies and design the appropriate solution. The other big considerations are whether or not it'll be human flight. So if you are conditioning physical space, it brings a different element to thermal and environmental control. So you have to take that into consideration. And then coupling those two first bullets, usually when you're in human space flight or you have very high power, you are going to have unique geometries and you're going to have long transport distances. So those will add to complexity and begin to favor more active thermal control. So with that, I did mention kind of the preference towards passive up to a certain level. And the primary reason for that is the risks associated with active systems. So anytime you have moving parts, mechanical components, you will have potential for failure. So the primary areas are pump failures, usually combated with redundancy in the system. You'll also have potential for weld joints, which are often go through very rigorous qualification testing, as well as fluid volume management, which we'll talk about with some of the accumulator technology. So kind of summarizing again the active components, this is very similar to any single phase pump system schematic you might see for terrestrial, but you'll have a pump, usually a space qualified pump with a very robust qualification and acceptance test protocols. As I mentioned before, usually you'll have N+1, N+2 redundancy on that pump to make sure that you can absorb at least some failure mechanism. You'll have cold plates or liquid lines to pick up heat from components. The transport lines for the adiabatic section from the components to the radiators. Ultimately, you'll reject heat through your radiator system, and then you'll manage your fluid volumes through accumulators to compensate for that working fluid. So now looking at some of the liquid-cooled radiators or cold plates, there's several types of designs you can use here. Very similar to passive systems, you have the options of a solid-state radiator or a honeycomb-based radiator panel. A lot of different trades off there from mass or machining complexity or cost, but from a thermal standpoint, you can embed liquid tubing into both options fairly easily, whether it's rigidly mounted or implemented into a groove structure or completely embedded within the honeycomb structure itself. There's also the option of vacuum brazing for cold plate solutions. But a lot of these trades are done from more of a reliability and mass standpoint, more so than a cost standpoint, which is usually the basis of design for terrestrial applications. And in terms of some of the industry standards that are very routinely flowed down on these type of systems, welding, similar to like heat pipe technology, which goes through the same welding standard. AWS 9 or D17.1 is a fairly standard welding process to adhere to make sure we have very robust joints and limit failures. And then most of these systems are helium mass spectrometry leak detected, as well as go through fairly rigorous proof and burst pressure testing. So at the end of the day, we want to make sure nothing being flown fails for something that's fairly minor. So they do go through fairly intense testing protocols. And once you have kind of the heat collection and transport mechanisms and the radiator systems designed in, the other area to take really strong consideration is the accumulator side. So as we noted here, the big principle here is to compensate for the density change. And as an example, you can see the difference in density of ammonia between a plus 40 degrees C and minus 40 degrees C setting. So there is a fair amount of volume change associated with these fluids as they collect heat and transfer heat long distances. So you have to be able to compensate for that in your system, and accumulator technology is a really kind of necessary way, but also has gone through a lot of fairly elaborate design cycles, so it is a pretty reliable technology at this state. There are several different kinds of accumulators. The one you see in the picture here is a bellows-style accumulator, which those bellows can kind of expand as the fluid volume requirement goes up and retracts as it declines. There's also heat-controlled and wicked accumulators, especially useful for two-phase solutions where you want to ensure that all your vapor is contained and trapped in the accumulator and that any pumping mechanism will not see any liquid vapor. And then on the right side, you can see a kind of short list of a lot of the testing that goes into these. So these go through pretty lengthy and elaborate qualification and acceptance testing and making sure that they are flight worthy at the end of the day. ACT has been flying accumulators with the support of NASA. We have accumulators on the ISS and other systems. So we have gone through these qualification and acceptance test cycles and have been able to pass through. And then one final area we wanted to talk about before passing it over to Jimmy is the idea of hybrid systems. So the original thought about when to make the trade from passive thermal control systems to an active thermal control system is a good starting point, but oftentimes there is benefit of looking at both approaches and ways to incorporate both types of technology into a system. This becomes, I think, more relevant in human spaceflight applications. So as noted here, there is somewhat of a desire on any surface or any area that's exposed to astronauts that you would have a water-based solution like a PGW as the heat transfer mechanism at that area, but then you could go to more traditional space fluids like ammonia on the external side of things. Also, again, there's ways for complexity to be greatly simplified if you don't have to route unique fluid geometries all over the place. So oftentimes we can use a more simplified single-phase loop to reduce the risk associated with failures in a single-phase loop, and then a more complex passive loop with loop heat pipe or constant conductance heat pipe technology to transfer heat out to the radiators and reject to deep space. So hopefully that gives some sense of when to consider and the trade-offs between active and passive. And with that, I'll pass it over to Jimmy.
Thank you, Brian. That was great. I'll be focusing a little bit more on passive solutions, but in particular relating to thermal challenges of the moon, both in orbit as well as on the surface. And the big question overall here is why? Why do we care about these thermal challenges? And the goal is to extend mission duration. So as we move through here, you'll see that there's a lot of thermal challenges both on orbit and on the surface of the moon. The moon does not rotate particularly quickly and also does not have an atmosphere. So the result is that one side gets really hot while the other side radiates all the heat out and gets very cold. So when you're in orbit, this can result in very large temperature swings, as we'll see here on the next slide. So as you're orbiting the moon here, this is our little spacecraft, this little orange one here in the center. You've got moonshine coming up from the moon, as well as radiation from the sun. And this plot on the right-hand side is showing the infrared loading from the moon. And as you can see at 0 degrees from the subsolar point, so closest to the sun, getting about 1,314 watts per meter squared. That's a lot of heat. It's basically a second sun that's going to be shining on your spacecraft. So when you're on that subsolar side of the moon in orbit, you're going to be getting cooked with basically 2 suns. And then as your orbit goes to the opposite side, it might as well be deep space. So very, very large swings in temperature as you're in orbit around the moon. Similarly, when you go to the surface, there's obviously dust challenges, but we're going to focus more internally within components that would be landers or rovers. But as the moon is slowly rotating, that means that your exposure to the sun is gradually changing. So starting from the sharp transition from where there's the red and the yellow and green gradient to this very large blue central region, that's the lunar night. And basically, as the moon is rotating, it takes 14 Earth days to go from that sunset to the sunrise. And if you look closely, it's very difficult to see on this, but as you get into the polar regions, they are particularly cold and challenging as well. So being able to drive around and operate, or if you're a lander, stay stationary operating during those lunar days for solar power is great, but then being able to hunker down for those very long lunar nights and accommodate those large temperature variations is quite a challenge. So there's a couple options on the surface. Obviously, number one is brute force. Bring a lot of power with you so that you can make it through that long lunar night. That's kind of the future that we'll look at here a little bit later, talking about nuclear. The other is to design your equipment, your lander, your rover, for very large temperature swings. It's landing site dependent. It could be swings from 100 Kelvin up to 300 or even 400 Kelvin in some of the equatorial regions. This can be a challenge, though, particularly when you're trying to do science, instruments in particular, being able to design for such large temperature swings, obviously coefficient of thermal expansion with different materials, lots of challenges there in order to make that work. Another option, and this is the one that we're going to focus on here, is protecting temperature sensitive components in a warm box. So gathering all those, whether it's science instruments, avionics, gather them all together in this warm box and then have a variable thermal conductance link to the radiator so that when it's daytime, you have high conductance so that you can reject your heat while you're doing science, and then as lunar night arrives, turn that thermal link off to have minimal conductance during lunar night so that you can hold the heat in and limit that fluctuation of temperature within the warm box. We're going to look at a few different hardware solutions. This first one is louvers, which is an orbital solution. This is a relatively brute force one. Traditional requires specific spacecraft orientation. You're basically shading your radiators to be able to minimize the solar loading that's occurring on them. But the next three we're going to take a little bit closer look at. The first being a two-phase thermal switch. The next being a variable conductance heat pipe. There's a bunch of different, we'll call configurations or flavors of variable conductance heat pipes. And then finally, we'll take a look at loop heat pipes with a thermal control valve. The two-phase thermal switch, this is the smallest of our options. It provides a high turn-down capability, and it's combining a, we'll say, more traditional heat pipe on the internal bellows. So as you can see the image more towards the center, This is the bellows being retracted. You can see the difference in the bottom from the center to the right-hand side. When it's retracted, the heat source is very little, and the working pressure of the working fluid allows that to be retracted. As the heat source increases, that allows the bellows to be able to make contact and then be able to make contact with the heat sink and be able to reject that heat. So very high turn down capability from on to off, and also high power capacity, carrying capacity for considering the small volume that it is. And here's a little test data for one of our thermal switches. So when it's in the operating condition, it's maintaining that fixed evaporator temperature, which is the top line here, the red one. As you can see, the power is constant, and the vapor temperature is constant as well. But this purple line is the condenser, which would be your radiator. And as the temperature is dropping, you can see that the switch is then making contact and removing contact in a high enough frequency ratio that we have steady control of the evaporator temperature, regardless of what the sink temperature is doing. Our second option, this is a little bit larger one. This is the variable conductance heat pipes. The one pictured here is a cold reservoir heat pipe. This provides passive temperature control, which significantly reduces survival heater power. There's both cold and warm reservoir options. Our warm reservoir has some flight heritage. It was on Peregrine, so rest in peace, but it did get up there. And we have some other options in addition to these. So max heat transfer capabilities are very similar to constant conductance heat pipes that you'll see in radiators. Hardware and construction is very similar with the addition of the gas reservoir on the end. So the gas reservoir on the end contains a non-condensable gas, and as the temperatures change and the heat load changes, so you can see on the top image, the heat going into the evaporator, those are the big arrows, that's indicating that it's on and a lot of power. The blue is the two-phase working fluid that allows the high variable conductance heat pipe to be operating in the high conductance mode where it's on. And then as the temperature and the heat load reduce, that's the little arrows on the image on the left-hand side into the evaporator. That two-phase working fluid retracts. The non-condensable gas comes out of the gas reservoir and blocks off a portion of that condenser to turn down the amount of heat that's then being rejected. And what that allows you to do is to maintain a steady evaporator temperature. The final one is loop heat pipes. This is the largest. It's great for deployable radiators. There's a wick structure that's located in the center of the pump body for collecting the heat. And we can do variable conductance through a thermal control valve, which also is passive in nature, which allows for extremely low survival heater needs, and is also great for being fully passive. One of the additional benefits of a loop heat pipe is that it's a diode mode, but it can go into diode mode as well. So if there is heat applied to the radiators that is greater than the temperature of the evaporator where the pump body is, that will prevent backflow of heat into your warm box. And one of the things that is also nice is that these can be designed to provide shock and vibration isolation for rovers. So taking a look at all three of them, we'll take a look at the manufacturing processes for loop heat pipes first. So there's three different ways that ACT fabricates these. Traditional, we'll look at the top and the bottom rows as kind of the two primary options. The traditional one is the top row, and that has the big H word, heritage. So music to all of our quality personnel that are online. So this is the traditional way of making them, very high performance, small pore radius, great thermal performance, but a very complex manufacturing sequence that requires long lead times and high costs. The new up-and-coming way to reduce lead time is the 3D printed loop heat pipe that utilizes additive manufacturing, where we print a lot of the very complex components of the pump body together into one part. So this really simplifies the manufacturing sequence, leading to a shorter fabrication process. And we're currently at TRL 5 to 6 and improving this relatively rapidly. Now we'll take a look at all three of them together to see where the strengths are of each of these three technologies. The two-phase thermal switch is really great into the 10 to kind of 100 watt range. This is the smallest volume and provides great on and off conductance. The variable conductance heat pipe, that is very similar to the constant conductance heat pipes with the addition of the non-condensable gas to provide the variable conductance, and is in the 50 to 500 watt heat range. These are nice in that they provide a gradual conductance change, but are very application specific. As you can imagine, the length of the evaporating section, the condensing section, drive how big the reservoir needs to be for that non-condensable gas, and how much gas it gets charged with is all very specific to the application, but when tuned appropriately to the application is a very great tool. And finally, loop heat pipes with the thermal control valve. This can do from about 100 to well over 1,000 watts, allow for that complex routing, vibration isolation, and maintain that source temperature steadily as the TCV switches back and forth, which we'll take a look at here shortly with the featured project. But one of the drawbacks is that it is a complex system with numerous parts. So the featured project that I'd like to go over is the NASA VIPER Rover. This is one that ACT has been working on for the last 3.5 years, from conceptual design through critical design review, through qualification, and into the flight build. We were responsible for the complete thermal management system of the rover, so both heat collection from inside the warm box, heat transport out to the radiators, and then heat rejection from the radiators. This is a very unique warm box assembly approach for being able to reject the heat during the lunar daytime as the rover is driving around and doing science, but then being able to use that variable conductance of the loop heat pipe with the thermal control valves to hold that heat in the warm box during that 14-day lunar night. So here's a look at the CAD. At first glance, it can appear rather complicated, but it is actually a very elegant and relatively simple solution. There's a lot of redundancy that is built into this. There's a loop heat pipe with a thermal control valve on each of the 4 faces of the warm box. That's the box that's in the center towards the bottom of the picture. And each one of those contains a bunch of embedded constant conductance heat pipes to gather heat from all of the components that are mounted inside of that warm box. And then as that heat is brought to the 4 individual loop heat pipes, they can reject the heat to the trapezoidal shaped radiators that are on the top there. And each one of the loop heat pipes is connected to the adjacent loop heat pipe through some crossing constant conductance heat pipes to provide additional redundancy. And on the right-hand side, you can see how this thermal management system, the big picture in the center is all the hardware that ACT was responsible for. On the right-hand side, you can see it with the additional frame, and then the integrated rover CAD below that, with the radiators highlighted there on the top. So VIPER Rover has two primary operating conditions. The normal operation of loop heat pipes occurs when the thermal control valve is above 10 degrees C. So heat taken from the warm box and brought right up to the radiator. And then the low conductance mode occurs when the thermal control valve is below 10 degrees C, negative 10 degrees C. So that's when we're keeping the heat in during the lunar night. This thermal control valve bypasses the condenser to maintain the evaporator above that set point and decreases the conductance accordingly. And as a result, the warm box temperature remains near that TCV switching temperature. So on this plot here, we have the thermal control valve. There's one inlet, and there's a bypass, and then what we call the primary on outlet. The red line across the center is the body average temperature. And as that temperature crosses below 10 degrees C, we can see that the flow then switches from primarily being the on outlet mass flow over to a roughly 50-50 mix around 5,250 seconds. And then as the temperature continues to drop and gets below negative 10, it is now in full bypass mode. So what does that look like in the whole system? The thermal control valve, we can see here on the left-hand side of the diagram. So this is showing the loop heat pipe with the thermal control valve and the radiator on top. So heat is coming in from the warm box into the evaporator pump body. The two-phase working fluid is then boiling off, and the vapor is leaving it out the bottom and going to the thermal control valve. During normal operation, the vapor then goes up to the condenser serpentine, where the heat is rejected out of the radiator, and the two-phase condenses into liquid, which then returns in through the top, through the compensation chamber and back into the evaporator pump body to then be able to pick up more heat. As the temperature lowers, the thermal control valve switches over into bypass mode, and that vapor that is coming out of the evaporator pump body is bypassed back into the compensation chamber, providing vapor into the pump body and preventing that flow of vapor up to the condenser to limit the heat rejection. This limits our heat rejection during the lunar night to just conductance through these very long, low thermal conductivity, thin-walled tubes that go to the radiator. So this provides a very high, what we like to call turn-down ratio, which is basically the on conductance over the off conductance, which is on the order of 100 to 1,000. Here's a little test plot we did in the lab here to verify the conductance turndown. The simple demonstration here on the top left, you can see that the evaporator average and condenser average, so that would be the warm box to the radiator, are very close in operating temperature. That means that the loop is picking up that heat and bringing it to the radiator and rejecting it very efficiently with that tight temperature range. We then were using liquid nitrogen on that radiator and dropped the temperature down as would occur at lunar night. And you can see that as the thermal control valve temperature began to drop, the temperature of the evaporator and condenser moved further and further away from each other. As that temperature got down to about negative 10 degrees C, we can see that the thermal control valve then goes into full bypass mode, and the evaporator temperature is maintained a little bit above negative 10 degrees C, regardless of what the radiator, that condenser average temperature is doing. So was stepping down from about minus 25 down to minus 50, and then later down to minus 80 without impacting that evaporator average temperature. And this hardware was all fabricated over the last, let's say, year and a half, tested, and delivered and integrated into the rover. This is a recent image NASA provided on the website of the rover build status. Can't see too much of the ACT hardware in here right now, but you can see a little bit of the edge of the radiators at the top there. Everything else is covered in MLI, but pretty exciting stuff to see it getting integrated for launch later this year. So what does this mean for you? Certainly draw on the insights from the NASA VIPER Rover, as well as numerous other lunar programs that ACT is supporting, whether it's in orbit on a lander or a rover. We can certainly help with some of the challenges here and help you select an applicable technology. Some of the things to keep in mind, of course, budget and schedule, as well as mission duration, mission duration, including whether it's number of lunar cycles or orbits, available mass and volume to help down select on which technology will be applicable, as well as temperatures for both operational and survival, and heat retention needs to help identify which one of these technologies is going to be the best fit, as well as redundancy requirements. So looking into the future, nuclear power generation. Why nuclear? This is the brute force method. This is the exciting one. So power all day and all night. So you can do science the whole time that you're there, but also the primary need is for allowing for continuous human presence. So anywhere from 1 to 100 kilowatts. And there's three primary major thermal components. There's the high temperature heat transport system that's bringing heat from the reactor to the thermal energy conversion generator, and then the cold side heat rejection system. So we're going to take a look at high level, high temperature heat transport system, as well as the cold side. On the hot side, the goal is to safely remove heat from the core. These are very high temperatures, sometimes well over 850 degrees Kelvin, and relatively long distance. And the cold side is all about transport and rejection of the heat. It needs to be economically scalable solutions and coupled to the cold end of the converting generator. So on the hot side, there's two primary approaches, similar to what Bryan was discussing. There's both an active and passive. Passive is king in that there's no auxiliary equipment, pumps, plumbing, valving, and then that N+1 or N+2 redundancy. Heat pipes are very simple and have very simple redundancy. And also they look super exciting, like these pictures on the bottom right-hand side when they're operating at these high temperatures. Just to give a little bit of perspective on what this looks like, this is from a NASA FSP slide showing here both the core and how it's arranged with the fuel and moderator and a bunch of heat pipes in this kind of grid-like arrangement. And these heat pipes are pulling the heat out, so there's many heat pipes that are embedded into this core and bringing that heat out to the power conversion system. So lots of redundancy and very simple, safe operation. ACT has been leading the way in hot side innovations, both on heat pipes, high temperature sodium heat pipes, as well as loop thermosiphons, as well as addressing startup and different materials. Ceramic is one that I'm pretty excited about for mass and being able to reduce the weight, particularly for space flight, is very exciting stuff. Looking at some of the ultra high temperature stuff, as well as some refractory metals and dynamic power conversion. This brings us, so this is what would be sitting on the surface. So this is taking heat from the power conversion device. It's collected and transported to the radiators. We have looked at light titanium water heat pipes with various materials for face sheets, both polymer, carbon fiber, graphite reinforced composites. These are very leading edge programs that are under development, looking at coefficient of thermal expansion mismatches, addressing those between the radiator phase sheets and the pump single phase loop, as well as taking a look at the structural integrity and getting these up to a point where they can be flight qualified. The exciting thing here is that this design using the heat pipes is very resilient, especially for micrometeorite impacts. Your pump loop at the bottom can be shielded and have very gradual, we'll say, elegant failure modes, so that if one heat pipe goes down, the rest of the panel is still operating and unaffected. And that covers it for nuclear power generation. And I'll hand it back over to you, Amanda.
All right. Thank you so much to both of you, Jimmy and Bryan, for the wonderful presentation. That was all very informative. And just a reminder to the audience, you can still submit questions for our speakers using the Ask a Question box on your screen. Now we can take some questions that have already come in, and we have several here. First off, for the two-phase thermal switches, how do you maximize the contact area? I feel like the contact resistance would be a large limiting factor, someone says.
Oh, yeah, that's a great question. So it's very, let's see, this is Jimmy here, aspect ratio dependent. So we try to design these around bellows that have heritage and getting that area high so that we can reduce that thermal interface losses. There's also some tricks that R&D are working on to improve the thermal resistance at those interfaces. Certainly something that we can discuss more offline.
All right, great. Thanks so much, Jimmy. Next question asks, when would you move to an active system for Lunar?
Yeah, hi, this is Bryan.
Yeah, that's go.
Sorry, Jimmy. It's a good question, and I think a lot of the trades would be similar to what we discussed earlier in the presentation for orbital opportunities. But a couple different caveats for Lunar. One major one being that there is some gravity. So that does open the envelope for things like thermosiphon technology, which can move higher, have higher heat capacity for passive operation. So in a two-phase system, a lot of the limitations on power capacity and distant transfer is related to the wick structure's ability to pump the liquid back to the hot end. So in microgravity, you're basically assuming somewhat of a horizontal operation from a heat pipe calculation perspective. But when you go onto a lunar surface, similar to items in a terrestrial environment for like HVAC systems, you can actually utilize gravity to your benefit. So in terrestrial systems, we've moved hundreds of kilowatts using thermosiphon technology, and that would be an opportunity to expand the limits of passive heat transfer and dissipation in a lunar environment. So the trades might be a little more favorable to passive if you have favorable operating conditions on a lunar environment.
Okay, great. Thank you, Bryan. Jimmy, was there something you were wanting to add?
No, that was great. Yeah, one of the things to also keep in mind is that there could be planned outages or we'll call it standby mode before the system is operating, where that would be taken into consideration for the solution as well.
All right, great. Thanks to both of you. Next up, someone says, can you comment on other types of fluids for liquid cooling you've used or looked at, excluding water or glycol type fluids?
Sure. Water, this is Jimmy. Water is a great one. Great heat capacity. It's kind of the go-to. Glycol as well to get that little bit of lower temperature range. But when it comes to pumped loops, there's certainly a lot more options for traditional refrigerants as well as floor inerts. But moving over to the capillary systems, so traditional heat pipes, loop heat pipes, and variable conductance heat pipes. We have what we call a figure of merit. That is a measure of how well a fluid can heat pipe. So ones that are more traditionally used in spacecraft would be ammonia. Has the next best figure of merit in comparison to water. Other ones would be particularly attractive for the moon would be propylene, as that then extends the operational temperature range down even further than ammonia.
All right, thanks, Jimmy. Next up, what is the maximum heat load for two-phase thermal switch?
Right now, I think the largest two-phase thermal switch that we've made is on the order of just under 100 watts. As the astute listener observed, there's that additional contact resistance as the bellows expands and makes contact. And once we start to get up around 100 watts, it really starts to become more attractive to look at variable conductance heat pipes to make sure that we still have a good on conductance.
All right, great. Thanks, Jimmy. And someone says, how do we implement one of these solutions?
Yeah, good question. This is Bryan speaking. Because all these are custom solutions, there is really a lot of co-engineering that takes place. So I kind of breezed over it, but our core values as a company are innovation, customer care, and teamwork, and we really try to embody those as we work with customers. So from a practical standpoint, we like to work with our customers to understand all the design requirements as thorough as possible, come up with very critical verification, analytical verification matrices, as well as hardware testing verification matrices, and just make sure we dot all the I's and cross all the T's as we explore new technology or even heritage technology and implementing into these practical applications. So yeah, a lot of, I would say, working together and understanding the system opportunities and the technology limitations, and then making sure that everything is well designed from a component to a system level.
All right, wonderful. Thank you, Bryan. Appreciate that. Next up, how do your VCHPs compare in terms of weight and volume to regular heat pipes?
Sure, very similar compared to traditional constant conductance heat pipes. The primary addition being that non-condensable reservoir that's going to get added on the end. And the size of that reservoir is going to be really dependent on both your evaporator and condenser lengths for how much that non-condensable gas is going to be able to block, as well as the temperatures of where we want that turn down of the conductance to start.
All right, great. Thanks, Jimmy. Next up, someone says, is there any possibility of partial or total failure due to mixing of gas and the working fluid in the VCHP? And are there any known failure modes?
Oh yeah, this is a tough question. So let's see. So we'll talk with the on conductance side first. So there's a lot of testing and analysis that goes into the chemical compatibility of the working fluid and envelope. to make sure that they're compatible for very long lifetimes. We typically design them for around a 15 to 20-year lifespan. And the addition of the non-condensable gas and reservoir is a gas being non-condensable. It's going to be very low reactivity. We tend to use inert acids, so no additional impact there. A lot goes into the design of the variable conductance heat pipes to ensure that the liquid of the working fluid is managed throughout the temperature range.
All right, great. Thanks, Jimmy. Let's see. How long can the heat pipes be for the nuclear power plant case?
That is a great question. I'd have to check in with our subject matter experts and see what the limit would be on that. I know that it's going to be on the order of meters, but we can certainly follow up on that one.
All right.
Yeah,
no problem.
I think just to kind of build on that, the limitations from a length perspective would be similar to, it's not specific to the high temperature heat pipes. It would be specific to heat pipe technology in general. So it would come down to a lot of the items Jimmy discussed when talking through the figure of merit, that being the surface tension of the fluid, the internal wick structure, the pumping against gravity height. So we need to understand the operating conditions and kind of design for the heat flux as well as much lift as you need in the system and try to come up with the ideal case there.
All right, thanks to both of you. Next up, can these solutions be used in LEO?
Yes, certainly. If there's a temperature sensitive component that you're putting into LEO, just because the conditions aren't as severe in LEO as they are around the moon, we can certainly still apply them to help maintain the temperature sensitivity of whatever that component happens to be. Much of the variable conductance heat pipes that we've designed have been for LEO. There's been a few additions for lunar applications as well.
All right, thanks, Jimmy. And I think we have time for just one more. Is there any place for plastics in these demanding applications, or is it all metal?
I guess I'd have to understand a little bit more about the application of the plastics. Our compatibility with the working fluid and envelope has been all for metal applications. One of the challenges with plastics is the difference in coefficient of thermal expansion compared to the metals that would be for maybe the working structure or the components, boxes that would be needed for conducting the heat out of the boxes. So certainly something that can be a challenge that we'd have to take a look at.
All right, thanks so much. Unfortunately, that is all the time we have for today. I would like to thank Jimmy Hughes and Bryan Muzyka, as well as our audience, for joining us. And thanks to everyone who submitted questions. I know that we didn't get to all of them live here, but we will be supplying those to Bryan and Jimmy so that they can follow up later. As a reminder, you can download a copy of today's slides under the Event Resources tab on your screen. In just a moment, a survey will pop up. Please tell us what you thought of this program by answering 3 quick questions. This webinar will be available on demand for the next year, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, I thank you all for watching.